Welcome to another session of Circuits and Networks. In today's class under GATE exam, this will treat as class 1 for transient analysis. In GATE exam, whether it is belonging to electrical engineering or electronics engineering, transient analysis under networks and circuits is a very important topic. So we'll see some of the basics and the problems which are asked in GATE exam. We'll also continue with our further classes pertaining to transient analysis. So let us start with the basic analysis. What is inductor and capacitor under transient behavior? So inductor, when it is combined with resistor in series with the switch and connected to a source, and the current flows into the circuit, and capacitor, the same arrangement when it is replaced by capacitor in series with resistor in series with switch with a source, then the current through the inductor or through the circuit is obtained in inductor is given by V input by resistance of 1 minus e to the power of minus R by L T, or this is also written as V by R 1 minus e to the power of minus T by tau. T is the time period and tau is the time constant. Here the time constant value for RL circuit will be given by L by R. So this we need to remember in the case of inductor. And how does we have framed this equation analysis? You can look into our previous transient analysis videos. In that, the derivation under differential approach, derivation under Laplace approach, it is derived. You can look into those videos and easily we can obtain the transient current for RL circuit when input is given as V in through a switch. So this is the equation of the transient current. And when you look into the waveform of transient current with respect to time, uh, according to this equation, you're going to get the exponential rising curve. Similarly, for the capacitor, when you account for transient current, the equation would be V in by R e to the power of minus 1 by RC t. Again, small t is known as the time period and RC is the time constant. So here, if at all you substitute the values of different values of t, you're going to get the output of transient current as drooping characteristics, or it is exponentially decaying. So this is how you need to remember the basics of capacitor and inductor under transient analysis. So these two formulas are very important for inductor and capacitor respectively. And again, in-depth knowledge of these equations you can easily obtain from our previous videos under transient analysis. Apart from this, remember the formulas for inductor and capacitor, that when a current flows through an inductor, the voltage developed across inductor is given by VL is equal to L di by dt, and the charge inductor behaves as current source. So we are framing this equation as Roman 1. Under capacitance, when current flows through the capacitor current is given by C dVc by dt. You can cross check over these two equations, Roman 1 and actual number 1, where you can see the voltage developed will be equivalent to L di by dt across inductor, and the formula for capacitor current would be equivalent to C dVc by dt. So this is how you need to take the catch, and this is how you need to remember the formula for differential formula of inductor and capacitor. And when the capacitor is completely charged, it behaves as a voltage source. So these two basics are important. Apart from this, once you are going to get the equation 1, I can easily obtain the value of current once I know the value of voltage across the inductor with this equation. So the current equation would be equivalent to IL is equal to 1 by L integral VL dt. So this I am framing as equation 2 under inductor as Roman 2. Similarly, the voltage across capacitor would be 1 by C integral IC dt. So these two are the other two basic formulas what you need to remember when you're dealing with transient analysis. Again, one thing to remember, integral in equation 2 can be separated as t equal to minus infinity to 0 and t equal to 0 to t, where this equation 2 is framed as IL is equal to 1 by L minus infinity to 0 minus VL dt. 0 minus indicate just before the switching case, plus 1 by L 0 minus to T VL dt after the switching case. So this is the equation for current for inductor. Similarly, we can apply the same logic for capacitor by taking integral in equation 2 and separating the t values from minus infinity to 0 and 0 to t, as Vc is equal to 1 by C integral minus infinity to 0 minus Ic dt plus 1 by C 0 minus to t Ic dt. So these basic formulas you should know before dealing with the transient analysis. Once again, I am reminding you, if at all you want to know the complete basics of transient analysis, look into our previous videos under transient analysis. You'll come to know how we have derived this kind of equations. Okay, with this basic information, let us solve the important problems which were asked in previous GATE exam. So in the first problem, which was asked in GATE 2021 for 2 marks, in the circuit, the switch S is in closed position for a very long time. Means what? This switch was closed for a very long time. If the switch is open at time t equal to 0, then IL of t in amperes for t greater than 0 is dash. In the sense, he wants to know what is exactly the transient inductor current. For this, we have to see the switching position, before switching position and after switching position. For example, according to the given options, you have A, B, C, D. If the switch was closed for the long time, this is shorting 4 ohms and 30 volts. In fact, you are left over with input 10 volts, resistor 1 ohm, and inductor for long period, it becomes short circuit. So this is the condition of switch when it was kept for long time, and this is circuit it is obtained. And if at all I want to know what exactly is the current before switching, so I'll name this as I of 0 minus, whose value will be equivalent to 10 amperes. Why 10 amperes? 10 divided by 1 becomes 10 amperes. And one of the important property of the inductor, that current through the inductor cannot change instantaneously. In fact, I of 0 plus will be equivalent to 10 amperes. This I am framing as equation 1. I hope you understood how we have obtained I of 0 minus equal to I of 0 plus as 10 amperes. Then, coming back to the problem, if the switch is opened at time t equal to 0, then the inductor current in amperes for t greater than equal to 0 is dash. For that, for t greater than 0, this is a circuit how it looks like. Because the switch is open, this upper terminal will go off and 10 volts is connected in series with 4, in series with 30, in series with 1, and in series with inductor. Now if at all the current has to flow into the circuit, I have to apply KVL to frame the equation. So I'll apply KVL to this closed loop. I'll get minus 10 plus 4 I of t, this 30 with negative symbol, so minus 30 plus 1 I of t plus 0.5 di by dt equal to 0. So you can see all the voltages in a closed loop is equivalent to 0, or satisfying the KVL formula, that is the sum of the voltages in a closed circuit is equal to 0. So this we have framed the equation. After framing this equation, let us rearrange this equation in a proper way, that is in terms of di by dt. So 0.5 di by dt, you have 4 plus 1 I of t will become as 5i, and you have minus 30 minus 10 which goes to the right hand side of this equation, it becomes 40. In fact, di by dt, I'll take the 0.5 denominator of 5i and denominator of 40, it will be giving you the value, the equation as di by dt plus 10i is equal to 80. Now this is a mathematical equation. So I'm framing this equation as 2. And what exactly the mathematical equation? It's a non-homogeneous differential equation of the form di by dt plus pi is equal to q. For this, the practical solution, or you can say the general solution of this equation would be I of t equal to e to the power of minus pt integral q e to the power of pt dt plus k e to the power of minus tt. So here we have taken the complementary function and particular integral, and we have framed the general equation according to the mathematics what we have learned in our in our basic first year engineering. Fine. After framing this equation, I'll take the equation 2. I'll take the values of p and q according to the given equation 2. Here the p value is 10, q value is 80, and I'll apply the formula for general solution. So I'm going to get I of t is equal to e to the power of minus 10t, which is the value of p, integral q is 80, e to the power of pt, that is 10 dt, plus k e to the power of minus 10t. Okay, now I'm applying integral to this lower part of the equation. So I'm going to get 80 by e to the power of 10 dt gives you the value as e to the power of 10 dt by 10, e to the power of positive 10 dt, positive 10t, and e to the power of minus 10 dt, they cancel out, and the denominator value is 10. So I'm going to get the value as 80 by 10 plus k e to the power of minus 10t. Now this equation further is classified as equation 3. Now I of 0 plus. From the initial conditions, we know that I of 0 plus is equal to 10 amperes. So I'm going to substitute the value of I of 0 plus in order to obtain the value of K. So K would be equivalent to 2. So framing this equation as 4 and substituting equation 4 in equation 3, we will be getting the value of I of t is equal to 8 plus 2 e to the power of minus 10t. So this gives the answer on option A. So this is how you have to solve for transient problems under RL circuit. In the second problem, which is shown in the figure 2, switch S2 has been closed for a long time. So S2 is closed for a long time. At time t equal to 0, switch S1 is closed. So this is closed at time t equal to 0. So at t equal to 0 plus, the rate of change of current, that is di by dt, through the inductor in amperes per second is dash. So similar basis of the previous problem, K 2016, under set number 1, it was asked for 2 marks. So go according to the data which is given in the problem. So first, S1 is open, S2 is closed, right? An inductor for long duration of time acts as short circuit. So in fact, this becomes open, and current I of 0 minus before switching, we are going to treat the value of I of 0 minus, which is flowing in this particular closed loop, and that current would be equivalent to 3 by 2 amperes. So this is the important part which we have derived. Again, inductor is shorted, so the value of voltage across inductor is 0 volts. That is for sure. Done. Now, after framing this equation as 1, let us see how the inductor will behave. As I told you, a charged inductor behaves as a current source. So you can see the charged inductor we have replaced with by current source. And as soon as the switch S1 is closed, inductor becomes open circuit. And this is how the circuit looks like. So figure 2, change it to figure 2a and to 2b. This is how it looks like. Now, looking into the circuit, practically we have a current source shared by 2 loops. And what is the value of the current? That is 3 by 2. So I have one node, I have 3 branches. This is one branch, this is another branch, and this is third branch. So I'll identify a node like this, and to this node I'll apply a voltage which is inductor voltage, and this is quite different from the voltage which is present in equation 1. That is a new value of voltage. So VL of 0 plus would be across this node. Remember, current through an inductor cannot change instantaneously, but voltage it can change instantaneously. This is an important point we need to remember in our minds. So let us derive what is exactly the value of VL of 0 plus. For this I am going to apply KCL at node of this figure 2b. So once I'm going to apply KCL, what I'm going to get? So I have node voltage as VL of 0 plus. So VL of 0 plus minus 3 by 1. This becomes one branch current. Another branch current it is leaving, that is the current source itself, that is 3 by 2. Then you have VL minus 3 divided by 2 equal to 0, thereby satisfying the KCL at this particular node. I have framed this equation. Now look into this equation. We have VL of 0 plus minus 3 as a common parameter. So I'm taking it outside. And this plus 3 by 2, I'm going to take it onto the right side of the equation. This becomes minus 3 by 2. So when I'm going to take VL of 0 plus minus 3 outside, I'm going to get 1 plus 1 by 2. So this becomes VL of 0 of VL of 0 plus minus 3 of 1 plus 1 by 2 becomes 3 by 2, and this minus 3 by 2 is on the right side. Cancelling out these two like terms, I'm going to get VL of 0 plus, which will be equivalent to 2 volts. How 2 volts? This becomes minus 1. This minus 3 goes to the right, it becomes plus 3. Plus 3 minus 1 becomes 2 volts. So this is how we have framed the value of VL of 0 plus. But exactly what we require? At t equal to 0 plus, the rate of change of current. We know that the formula for inductor, as I have already told you, that L di by dt is the value of voltage across the inductor. So L di by dt of 0 plus will be equivalent to 2 volts, and the value of inductor is given as 1 Henry. So di of 0 plus by dt is equal to 2 by 1, which is equal to 2 amperes per second. So this is an interesting problem under initial conditions for RL circuit. So this is how you need to solve the problem. I hope you like this particular problem. And into the basics, if at all you want, you can go to the previous videos and check out to the transient condition with initial conditions. Okay, now we are done with RL circuit. Let us go with the capacitor circuit. Uh, in problem 3 under GATE 2019 for 2 marks, a problem is framed in such a way that a 0.1 microfarad capacitor is charged to 100 volts, is discharged through a 1 kilo ohm resistor. The time in milliseconds, we have to round it off to 2 decimal places, required for the voltage across capacitor to drop to 1 volt. So how to understand this problem? So first look into the problem. What are the conditions which are given? The condition was given that the capacitor which is of 0.1 microfarad, it is charged to 100 volts. So let me treat this value of voltage as V0, that is 100 volts. Now this charged capacitor is discharging through resistor, right? So from the given data we conclude that it's a first order RC circuit and it is discharged through resistor. Therefore V of t could be equivalent to V0 of e to the power of minus t by tau. Now since it's a first order RC circuit, V of t equal to V0 of e to the power of minus t by 2. If at all voltage was given of some particular value, then the formula of discharge current, discharge voltage through the resistor would be given as V0 by R. Since it's a first order RC circuit and the capacitor is charged already, so this equation goes to V of t equal to V0 of e to the power of minus t by tau. Small t is the time period, tau is the time constant. Now from the given data, V0 is charged to 100 volts. So V0 is 100 volts, right? Now we need to know what is e to the power of minus t by tau. Tau is the time constant. So from the given circuit, the time constant is equivalent to R equivalent into C. So R equivalent value is given as 1K and C value is 0.1 microfarads. So I'll multiply these two and I'm going to get the value of time constant as 0.1 millisecond. Now I'm going to substitute this value in this equation. So it becomes 100 e to the power of minus t by 0.1 millisecond. In fact, milli I'm going to take it into the numerator of this equation. So it becomes 100 e to the power of minus 10,000 t. Now this is the equation what we have framed according to the given question. But what is the requirement? The time in milliseconds required for the voltage across capacitor drop to 1 volt. So this voltage is dropped to 1 volt. So the same equation I'm going to take and I'm going to equate it to 1 equivalent to 100 e to the power of minus 10,000 t. Now it's simple mathematics. 1 divided by 100 will be equal to e to the power of minus 10,000 t. So this will give you the value of e to the power of minus 10,000 t equal to 0.01. In fact, apply the logarithmic value of this equation. I'm going to get 10,000 t equal to ln of 0.01. Then t would be equivalent to 0.46 milliseconds. Isn't that simple? Just we have applied the simple mathematics. We have applied the ln on the both sides, and after that we have applied the value of t, which is nothing but this constant divided by 10,000, whose value will be equal to 0.46 milliseconds. It's a very interesting question. So this question is given in GATE 2019 for 2 marks. Let us go to the another problem which was framed based on GATE 2016 under set 2 for 2 marks. You can see the same problem, but the problem is changed from a simple direct circuit to a switch S1. So in the circuit shown below, the initial capacitor voltage is 4 volts. Okay. Switch S1 is closed at t equal to 0. Fine. The charge, that is Q, in microcoulombs lost by capacitor from time t equal to 25 microseconds to time t equal to 100 microseconds is dash. So you can see same gate question was again framed for 2019 on the same concept. Okay, so I can say that this is a depth knowledge of the question of the previous third question. This is in-depth knowledge. For that, what we have to do, we need to know that the formula for voltage, that is the voltage is equal to V naught e to the power of minus t by tau. Now assuming that this is the first order RC network, so this is the actual equation of the voltage. Now it is charged to 4 volts, so that is why V naught is, we are taking the value as 4, and again e to the power of minus t by tau. Now calculate the value of tau. Tau is very simple. Tau is nothing but R equivalent to C. So once the switch is closed, this 5 microfarads and you have 5 ohms. So 5 into 5 into 10 to the power of minus 6 will give you the value as 25 microseconds. This is the value of tau. Substitute this 25 microseconds in this equation. I'm going to get 4 e to the power of minus t by 25 microseconds. In fact, 25 microseconds, this micro I am taking on to the numerator of e to the power of term. So it becomes e to the power of minus 40 kilo t. Now the charge across capacitor is Q of t equal to C V of t. Substitute the value of C, that is 5 into the power of minus 6, and V of t is nothing but 4 into the power of minus 40 kilo t. So this becomes minus 40 kilo t, and after framing this equation, I'm going to get the actual value of Q of t, which is equal to 20 e to the power of minus 40 k t microcoulombs. Now take the value of t of 25 microseconds. So at Q of t at 25 microseconds, the value would be 20 e to the power of minus 40k into 25 into 10 to the power of minus 6. So this becomes 20 e to the power of minus 1. In fact, 7.375 microcoulombs. So this is the value of Q of t at 25 microseconds. Right? Now the same value at 100 microseconds would be equivalent to 20 e to the power of minus 40k into 100 into 10 to the power of minus 6 becomes 0.366 microcoulombs. So this is the difference of initial charge and final charge. What is the requirement? The charge lost by capacitor between these two time intervals. So it would be 7.375 minus 0.3663. So this would be equivalent to 7.0087 microcoulombs. So I hope you understood this particular session, and we have selected only the basic problems for inductors and capacitors under this class, and I'm treating this class as class 1, and we have selected a problem which is asked in GATE 2021 and GATE 2019 pertaining to these two. Again, two more furthermore examples we have sorted out. I hope you like this class, and please share about this video among your friends. Subscribe to my channel and please press the bell icon for the future notifications. Thank you.